actually local to the area, so it was very possible to get you on relatively short notice, so that was great. So Nadia actually also grew up here and did her studies in Barcelona, the University of Barcelona, but did her PhD in the University of Cambridge. She got her PhD in 2015, then went to Caltech for a postdoc, and followed that with a RANE fellowship in the Netherlands at Radboud University. And since 2022, she has been back at the University of Barcelona as permanent staff with an ERC grant. Her research interests are binary evolution, transients, time domain astronomy. She's also done some instrumentation in that area, and most of her observational work is in the optical and infrared. And today she will talk us about some of her more recent results. Okay, welcome.
Yeah. Thank you very much for the invitation. It's a pleasure to be here. And yeah, just a small tip about my name. So it sounds complicated, but Nadia, it's easier. But then if you know my topic of research, which I read, you will remember my surname is Blago, almost Red Novae. Okay, so really there, so we are getting close. Okay, so yes, today we'll present you about binaries. That's my focus. And what can we learn about binary evolution from astrophysical transit? So first of all, of course, we need to show, a beautiful AI-generated image, that shows that stars are the building blocks of our universe. And that's how it is, right? Like if we want to understand our universe, we need to understand the most essential components of our universe, which are stars. And why is that? Well, there are like several reasons, like, of course, we know that stars make heavier metals and they enrich the material for the next generation of stars. Also, they are source of high energy particles. And also these materials also feed back into the composition of the ISM. But this is if we look at like single stars. Now, how can we make this picture more realistic? Well, we put binary stars. We have the same picture, but we have our universe formed not with single stars, like we can think by looking at our sun, but made of binary pairs, right? Binaries are essential component of the universe, and I would want to convince you why, right? The same components, like chemical enrichment of the universe, but what are the chemical importance? Well, for example, like when a supernova, all the iron, most of the iron. Like strip core collapse supernova. Okay, when you strip a star, the final explosion changes, the yields change. The neutron star mergers also come from binaries, and they give you the gold and heavy metals that we need, to make our way. So also strip stars, they are source of ionizing UV radiation, which could have played an important role at early times of the universe. Into their ionization, they are source of cosmic rays and supernova feedback. And finally, binaries also shed a lot of material into the ISM, so they can change the chemistry and the yields of dust. And that can alter also the astrochemistry, and affect how we can generate light. So binary evolution essentially changes how a single star evolves. And we all know that, right? Like having a companion really can change your life. So let's see a little bit more on the details. Right? So we start all, there's like studies, maybe not so recent, but they claim that by studying young stellar objects, there is a clear emerging evidence that most of star formation happens in binaries or multiple systems. Right? All the stars have siblings or have multiple siblings. So there's a lot of binary fraction or multiplicity fraction is very high at birth for different primary stars. So let's see what happens later, as time passes. And here I have like a little cheat sheet, this is the primary star mass. This is how long each mass is going to live, right? So we see there's a huge difference between the more massive stars and the least massive star. And this is for reference like a galactic year, a time that it takes to take a circle around our galaxy. And voila, we keep, this initial binary diffraction for the most massive stars. Because they're born, they start to move, they're dead, But like, of course, the small stars, they have, time to go around and circle, interact and start their clusters and lose their siblings. Maybe when you have a brother, you're very close when you're children, when you grow apart, like everybody goes on their own way. And this happens to these stars. The more they grow, the more they circle, the more separate they are. So, they're going to lose this binary diffraction. And so nowadays, this is what we observe, that massive stars tend to be in binaries, and this is likely because they still preserve their birth, multiplicity fractions. So this is cool and all, but like what's the story? Like, why do we care about that? Well, we don't not only care because master stars have siblings, but we also care because they will interact with their siblings. Right here is a plot, that shows that in each period, what is the fraction of those stars for different masses, 30, 10, 3, and like slow mass, and where they are. This curve is all the components of the system, and this thin curve is the inner. And this is an important point that they will interact with. Everything which has a shorter period than this will interact with a companion, right? So this is a major point, and that's why we care about binaries. Especially in massive systems, they do have binaries, they do have siblings, and they will interact with them during their lifetime. And this is important because they will, change how the universe looks. So why do we care about this? What are the pathways that makes us care more about that? Okay, well, normally you're born with a sibling, and well, generally one mass is larger than the other. So it will start evolving first, we will see that, and we'll start transferring mass. And what are the possibilities? Well, first possibility, we strip the star. This is a stable mass transfer. You transfer part of your envelope to your companion. The companion may invert the mass ratio, may become more massive, and this star will end up with a stripped, kind of very hot helium, mostly core. And this is important because very recently, in 2023, there was this study which found actually these stars. In the previous, we had like very low mass, like subdwarfs and like these Wolf-Rayet stars, which were stripped through winds. But these guys are this intermediate regime, which has been stripped by companions, right? So they start transferring mass, and then when they start stripping here, they go into the UV regime. This is super hot. So people could not find them because they were in the UV, and we barely have any UV data. I mean, hopefully this is changing in the near future. But these guys were hiding in a regime which we are unable to observe from Earth. So recently we found them, and this is the question, right? Like this could have been existed also in the early universe. So they make a lot of UV ionizing radiation. So this could have really impacted, early time universe evolution. Okay, a second chapter, stable, unstable. So if you go unstable, basically what will happen is like, you will fill the whole system with mass, and we will enter what we call a common envelope evolution. And in this regime, you can like spiral, transfer some orbital momentum, we will see this, but in the end, you have two outcomes. You can bring a secondary companion into the star and try to eject, outer parts of the envelope. Like when you switch a blender, like the material rotates. If you don't have a glass where you make your smoothie, your kitchen will be a mess, right? So this is what happens. If you manage to eject all this envelope, you have a compact binary. If not, you have a merger. And again, like this merger, it's a more massive and rejuvenated star. It has a huge input of all the fresh hydrogen, right, that it received from the companion. So it becomes a more massive star. Again, it has a UV emission, can alter cluster dynamics because it's a more massive star than the IMF, for example, and also can alter the supernova timing. It rejuvenates the star, so it may explode a little bit later and make different chemicals. Okay, so this is for the merger, and this is for the tightening, right? So through this common envelope, because of the drag forces, a very expanded binary shrunk to a much, much shorter position. And this is a very important mechanism if we want to kind of achieve any sort of excitement in astrophysics, right? We need to shrink binaries so that they can interact in a heavy way. Okay, so by doing this, the binary has shrunk, the envelope was removed. And there are recent studies that explored, for example, the outcomes of supernova from strip stars. And it's smashing, it kind of agrees more with like LIGO prediction, with shear masses and so on, but mostly it affects whether we will have a supernova or we will go in direct collapse. Again, this is important. We'll have a yield from the supernova, or everything will be like shrunk into a black hole. Also, the ejected mass and the composition changes. We have more hydrogen, less hydrogen, the chemistry in the ejector changes. And finally, also the amount of, like, for example, do we have fallback or it's a direct collapse, is also changing the mass distribution of the remnants. How many neutron stars do we make? How many black holes do we make? what are the masses of these black holes. So all these can be altered by the binaries, and also the amount of envelope that is left in the supernova when it explodes also can alter the kick distribution, right? So if we had the binary, then it can receive more or less kick, and a big kick can disrupt the binary. So finito, this is the end of our story. But if not, we can keep doing things. This is a bit similar to the previous phase. In this case, the companion can also expand and start mass transfer. We can enter through a second common envelope evolution that can go into merger, or if we shrunk even more the binary, this can go into a second core collapse, which can finally generate a binary which is at close difference that gravitational wave shrinkage can take place within the edge of the universe. So yeah, in this case, the binary evolution may define the masses of these compact companions, neutron black holes, what is the final separation, and who will, merge here and who will survive and go into this channel. And basically, this hugely impacts, one of the larger unknowns that we have now, like which is the merger rate of one of these things, like how many are merging in the volume. You look at the papers right now, 3 orders of magnitudes of uncertainty on the merger rate of neutron stars, for example, so we don't know because we don't know anything. And finally, the chemical imprint of the binary. If we merge 2 neutron stars, we make gold. Yay. If we make 2 black holes, what do we make? I don't know. A bigger black hole. I don't know. So then there is no enrichment. So there is no gold going in our, future forces minds. Okay. So then this brings the importance of understanding this. These all are possible unknowns, like how stable is mass transfer, this process. How many stars go this way? How many stars go this way? Then, when you enter this phase, like how much of this envelope is ejected? What are the mechanisms? How efficient we are? Are there extra energies that help us to get rid of this so we go down this channel? So, what is the final remnant? So all of these things are big unknowns, and all these unknowns through the process, as you see, this is the end. You carry all the unknowns with you until the end. So your final rate is 3 orders of magnitude uncertain. Well, at least we have somewhere where to explore. Okay, so but I want to convince you that we are in luck. So we actually have some observational evidence that can shed some light on these binary uncertainty processes that I have described before. And this is my favorite topic of research. And these are transients, astrophysical transients that we call luminous red novae. Right? And we have some evidence that I will show that they are associated to this phase, right? When you eject part of this envelope, think of this is very peaceful. This is not a supernova. This is like a very, very quiet and peaceful ejection of the outer layers. There may be some heating, some shocks, but at the end of the day, there's nothing exploding. So, the material can cool down very efficiently so that it becomes very cold and red. And that's why they're red. So why they're interesting? Okay, that not only tells me how this material was ejected, about this envelope ejection process, but in the modern day era, right, what we can go as well is to go backwards, for example, 10 years. And right now we have good surveys like, HST and other ones that have actually imaged that galaxy area before with relatively good resolution. So we can actually find, in some cases, the progenitors of those systems. And this is cool, because we know that something merged, and that means that the binary was unstable. So we can actually go back and study that binary. We can see what color it was, what evolutionary stage, what was the luminosity, and so on. So that can give us information about what was the initial binary configuration that led to that instability. And this is important, again, to quantify which, channel things go. And also we can monitor this thing now that we know that it's there, like for several years. And then we can see what kind of dust, for example, forms in that system, how much of it, on what time scales. And when we have more and more objects, we can actually kind of bring back all these things together, what binary went unstable, how much did it ejected and how, and what was the remnant of that thing. So it can start to give us some clues. So a little bit about these luminous transients. As you can see, this parameter space, this is like 10 days, they about 100 days, 200 to a year, sometimes duration. And they are what in the so-called the luminosity gap, right? Here we have core collapse, thermonuclear supernova, which are terminal explosions, and here we have no, like explosion on the surface of a white dwarf, which doesn't disrupt the white. But these are basically in the middle. I mean, as you can see, it's a banana. It's not really a gap, but we like to call them this way because most of them are in this gap. Okay, but yeah, we have, as you see, objects which are fainter and objects which are brighter, and that seems to correlate with the progenitor. Okay, so why do we say, and why do I so firmly claim that luminous red nova are associated to a merger? Well, we have only one event, only one so far that we have very clear signature of what happened. And this event erupted in 2008. It was from the Ogle survey that looks kind of for microlensing events in the bulge. It has very, very good photometric accuracy. So if you have seen enough light curves and you see this and you say, oh, but Ogle is better than that, right? Why is all this? What is all this crap? But then you think, oh, yeah, it's actually intrinsic variability in the star. It's not like I measured it wrong because these people do things very right. But then there should be something changing. So let's find the period. That's what you do. Do this. And the authors of this study that did that, right? They folded the period in different times. And what they saw that the shape was very similar to these UW stars, which are contact binaries. And basically, the most interesting thing is that before this burst, the period declined exponentially. So it was a binary, it was rotating, it was a contact binary, faster, 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 and boom, then we saw the nova. So this is really a proof that these events are associated to mergers. There were also some studies using pre-outburst imaging, which say was like, the donor was a 1.5 solar mass with a companion, which was like more or less like 10 times less the mass of the donor. So yeah, this was a contact binary, and the donor was slightly puffed up. And that means that it was evolving off its main sequence. And why this is important? Well, here we have some, this is an HR diagram, evolution of a 5 solar mass star, and this is how the radius evolved, right? So we are here at the main sequence, the star is happily burning hydrogen in its core and so on, many, many years, but then it starts to run out. Oh my God, I need to get energy, so I'm going to shrink. Okay, so it shrinks, but then, we achieve enough temperature to ignite hydrogen shell burning, so then the star starts to expand. And this is this case, right? Like when at the end of the main sequence, the post-main sequence phase is this green phase, and it's basically this, right? So during the main sequence, the star increased its radius by just like a factor, I don't know, maybe 2 or so, like it increased by factor 30 after the main sequence. And this is like almost instant in the life of a star, right? Like this expansion towards the red giant. Of course, we will contract as we burn the helium, but then KC again, we will finish that, the star will expand again. So being post-main sequence means that the star was actually here, which was in case B. So let's have a look at how the actual binary would look like. This is like a 3D potential model for the two stars, and one is the main mass, and two is the little mass. So here you have the rough potential, right, which say basically where the potential of each binary is in this co-rotating frame. So the thing is, if this star is expanding after its main sequence, its radius will increase, and this is like a cut like that. This is from the top. When the radius reaches this point, this is the Lagrange point number 1, we see that the star will experience a Rorschach overflow, right? The material will start, going into the neighbor, right, through this L2. If we keep, increasing the size of the star, it will reach L2, and finally it will reach the outer lobe overflow. Yeah, the outer lobe. So it will experience outer lobe overflow. And what we say that, well, I mean, it really looks like the star is doomed. If the mass is spilling from everywhere, every tiny bit of mass that a binary loses has angular momentum. So if the system loses mass, it loses angular momentum, so the binary shrinks. So basically, like here, and especially here, is like a massive loss of angular momentum. So if the star gets to that point, it will shrink and it will merge, so there's no way practically no way to survive. There are some studies that show maybe, but it's like very unlikely. Okay, so how is this mass transfer? Right, like just put some analogy. When the star expands during its main sequence, it's case A. So it grows in size. Yeah, it grows. But it's so slowly that even if it starts to exceed its Roche law, right, and it starts to transfer mass to its companion, this is a leaky faucet. Point, point, point. What do you have when you have one of those? You put like a bucket and you put the toilet. I don't know, whatever. You can do something with it. So the companion also can do something with this little bit of mass that's been transferred. So usually this is stable. But case B, oh my God, no. This is like this. If you have this in your toilet, please run away. There is no way to handle it because like case B, the star expands so quickly, right? That the amount of mass that is transferred through L1 is huge. So the companion usually does not have any ways of accreting, expelling, or doing anything with them. Right? So then everything will fill up. L2, L3, the system will start losing mass and the shrinkage and the final merger will happen. Right? This is like normally a terminal condition in the binary. All right. So if we look at our luminous red nova progenitors, as I mentioned, we have HST and other surveys. So where do we find these progenitors? Well, at least I'm pleased to see, that some of our expectations are accomplished. Like this is the main sequence, we start evolving, this is the red gem branch, and the black points are basically are the locations of, of our progenitors that we have observed in normally external galaxies, right, using HST data. So we see they're all yellow stars, they're yellow giants, supergiants, which are post-main sequence, so their experiences this dramatic increase in radius, which leads to mergers, which we believe luminous red nova are. So, okay, so here, until here, like all cool and more. But then you tell me, wait, you showed that diagram, right? That it was a case B and case C mass transfer, which also was like very steep. Where are the evolved donors, in that case C mass transfer? They should be over here. Well, there's a little bit of problematic question because, when you reach case C, the star is very expanded. It's kind of AGB stuff, and we know AGB stars make dust and all that kind of stuff. So imagine if you have a companion with that hose, showering you with mass. Obviously, that mass will go everywhere, right? And that mass will likely, some of it will get unbound and will cool down and will make dust. It can accumulate in a torus, it can accumulate in a shell, we don't know. But the point is there are some models that predict that basically these stars at the time of the merger will have a high extinction, right? This is an extinction of like 1 magnitude, this will be 10 or up to 100. So then the predictions are that by the time you reach your instability, you will be hidden by dust, right? There is so much mass just flying around, like from this binary transfer, that you will actually be enshrouded by dust. So if we look for luminous red nova in the optical surveys, we will not see them. So these are the expectations. So that's how we explain that we don't have any progenitors here. All right, so quest number one. So based on this information, with my team, we, for example, tried to say, okay, if we know these yellow stars, when they transfer mass, they're unstable. All these progenitors that you tell me, they're HST points like megaparsecs away. That's very hard to study. Can we find some of them in our galaxy? Okay, well, that's what we tried. We look for, for example, Gaia data. We look like stars here in the middle, like this yellow stuff, and which could potentially be mass transferring binaries. If you transfer mass, there's lots of like hydrogen there, so probably there's emission lines. They're probably variable. All these accretion happening. And perhaps there is this mid-infrared excess corresponding to all these materials that are like far away and cooling down. So we characterize them, and it's a bit disappointing. And this is a lesson that we're learning in a hard way: is that when somebody tells they took care of the extinction in the Milky Way, don't believe them, right? Don't trust. Because when we took spectra and we corrected the position of some of our stars, the red ones, they all resulted to be like, BE stars, like hot, young stars. So then they released a new version of this catalog, which took better care of extinction. Well, perhaps, these are the new data points. They look like more in the blue. But the point is that extinction is not trivial, okay? Even when somebody has Gaia is horrible, like, yeah, Star Core Boost, they're making improvements toward that, but it's very difficult. It's a very difficult problem. So doing anything in the Milky Way, hard problem. I mean, yeah, with the estimate of the masses, we also try to see which ones of those. I mean, the yellow ones are actually yellow through spectra. As you can see, they're minority. We didn't find that many. Most of them are blue. They're just extincted, and we didn't know about them. But some of them, like in this part, they're supposed to be filling the rush load, so transferring mass, and in this part, they're supposed to not. So, I mean, we have some candidates we are planning to explore with radio velocities, because you really need radio velocities to estimate the masses and finally define if they're mass transferring or not. But yeah, I mean, this is one possible way to go. To look what's in the Milky Way, what is yellow. If it's yellow, likely it's going through this Hertzsprung gap, growth, and it's likely will become unstable. So we can start through here. Okay, so what else can we do? Well, we progenitor, for example, was here. This is an extragalactic system. We found it. We have some HST photometry. We can model the SCD. We can get the luminosity, the effective temperature, and yeah, again, like it's sort of here in the middle, in this yellow regime, in like the KSP mass transfer. What can we do? Well, for example, you can try to learn more about what was the initial time that got there. And to do that, you need detailed stellar evolution models. For example, MESA is offering a model where you can initialize your primary donor, you can initialize the mass of the companion, and at what distance, what is the period, which is the binary distance, where they will start interaction. And then you can see what happens. In these cases, we found matching tracks. And you can see when the mass transfer starts, all of these binaries, they decrease in luminosity. Right? Why this is happening? Well, basically, stars need to respond to mass loss, right? The mass loss has been taken from them, so the stars lose it at hydrostatic equilibrium and needs to readjust. So it readjusts by generally expanding, if the envelope is radiative. So it needs to actually do some work internally. So there's less energy, in the nucleus to actually power the luminosity. So the luminosity drops in these cases, until, quite low values where mass transfer rate can be like very high. This is like 10 to the minus 1.5. Yeah, so in this case, we expect them to become unstable. So this is one of the works we did to try to see what progenitor masses we could get. And there is an agreement, right, that if we just take a single star evolution and we match it to the location of the progenitor, it looks like the star was less, like it was like less massive. If we account this loss of luminosity due to like readjustments, then basically we can have way more massive progenitors for that binary system. And this is important because it can actually tell us like what realistic progenitors that system could have had, before the merger. So the next step is also to think about instability criteria, right? We not only want the track to cross here, but actually we want the system to be unstable. So for that, we kind of introduce some of the criteria. I mentioned before the outer lobe overflow. So what we say is like when this donor mass grows in radius and the radius gets to the point of this L3, the outer lobe overflow, as I mentioned, this is kind of a terminal condition. The mass loss rate is so high that the angular momentum will shrink the binary, so the system will be unstable. And there's other criteria, and the quasi-abatic ones, for example, that we also employ, but we then search, this is now our new radius for the corridor. So we search for unstable tracks within that radius. And this is actually helpful because it can constrain more like with which parameter space of original binaries gave place to our system. And one important point is that what we see here, it's called delayed dynamical instability. And this is important it has a strong implications for other fields, right? And because when you want to go through this common envelope or a merger, you are not starting there. You are starting here. Like from this point of start of mass transfer to the moment when your binary became unstable and likely experienced the common envelope, your donor star lost already several masses, of gas. So the structure of that envelope, the mass of the envelope that you need to eject with a companion has changed. So basically, if you just assume a single track, this star has a lot more envelope, than something that has been stripped by its companion at the time of the merger. And this can influence whether it's going to be successful or not successful, whether it will merge or fully ejects, so it has a direct implication on the survival rate of compact binaries. So what other things can we do with MESA, for example? So it's very interesting because MESA, of course, provides you the density profile inside the star. So let's say for every radial coordinate, you know what is the mass. So then you can also compute what is the binding energy of each layer of mass of your star, right? And then you can use this formula, which is quite common in this common envelope, and you say, okay, if I use the angular momentum of my binary orbit to eject this envelope, basically I look what is the initial orbit of my system and what is the final orbit, and I will invest, a fraction. Let's say fraction 1 is like I'm 100% efficient in investing orbital energy into ejection of the envelope, so I want to unbind it and I want to give it some kinetic energy, because we look at this luminous red nova and the material is flying away with like few hundreds of kilometers per second. So, I mean, there is some kinetic energy to this. It's a bound material which is traveling, so it's not like we only unbinding, but we also like giving that a little bit. So if we have the binding energy of this envelope, we can trace this mass. As you go from the surface of the star into the star, we can see what is the binding energy of each layer of this star. And then for different mass ratios of companions, right? Like different, the Q is basically like the division because between like the more massive over the least massive. So how many times the donor is more massive than the companion. We can actually see how much mass we can eject with different orbital energy, right? So then we can estimate for each event, if we're capable of making the MESA model, we can estimate how much mass that binary could have ejected. So what do we see? Well, some of the results is, of course, more massive companions, the Q are less. They eject more mass, this is the case of the higher Q. But in all the system we have observed, they are very in agreement with B1309 scope. We saw the period decreasing, and that was a merger. In all these systems, we see that the ejecta mass is always under, it's always less than the mass of the envelope of our donor star. And that means that, the companion is spiraling, is like doing its work and so on, but it never gets to the core, so the envelope, it never gets fully ejected. And finally, the companion merges with whatever is remaining of the envelope and the core of the primary star. So at the moment, we see mergers. Okay, where are the full common reactions? Well, we are on a quest. All right. So where is this material? We talked that we are transferring mass and it goes to the binary. And, one of the things that we saw in this event before that I presented is that not only there is scatter, but there's also an increase, right, in the light curve. So not so recent, I think, simulations show that if you lose mass from L2 and the binary starts to shrink, like the velocity of this gas kind of starts to increase as well. And you can have some, ejecta from this, like spiraling around the binary and also causing like self shocks and like some intersection and shocks that can actually power some extra luminosity in this transit. And so we attribute this gradual increase in the luminosity just before the merger to all this material that the binary is losing through L2 and possibly L3 and whatever, points it has to lose mass. And because, this material is still kind of bound by the joint binary potential, like some of it may fly away, but it's mostly like in a torus, around the binary. So because of the intersection, it can radiate. So it can help us to explain this part that we see in this object. So in the case of the 1309 score, for example, they actually used the period and this signature to predict, right, how the mass loss would evolve with time just before the merger. So as long as the little, the L2 is behind the little companion, less massive companion, start losing mass, well, it starts to progressively increase the mass loss and obscure the little component. So then this would change your light curve, and that's what they see. So it's very valuable to actually have pre-outburst, really good photometry, because then you can actually see, how the period is decreases. And then you can model this mass loss rate and how it increases and how it carries angular momentum of the binary until the final merger. So it's not only these objects. If we look at nearby galaxies, M31 and 101, wherever we have like deep enough photometry, we all see that before the main burst here and here, 5 years, like 2 years, years to peak, we all see that these luminous red nova, they always have an increase, So this precursor emission, like associated to this copious mass loss, it's conspicuous. It's always there, right? So then if it's always there, next question we can say, oh, look. So, would we just look for systems that, increase in magnitude just to kind of catch them before the outburst? Well, we're trying to do that. Difficult again. One of the things that we did is quest 2, look for these sources in our own galaxy. Again, extinction. Yeah. We selected the Hertzsprung gap, we looked which ones would be variable and increasing steadily. We characterized, meaningful radiuses and densities, and we looked at emission lines. Most of them had emission lines, which was like, oh, great, perhaps they're interacting binaries, they're going to merge. Until we obtained spectroscopy, and that was like a big woof, because we saw all of them had helium-1 lines, and these bimodal thingies that B stars have a lot. So when we use spectroscopy to, again, correct for extinction, all our beautiful yellow giants and supergiants were just extincted B stars. So we have a beautiful sample of 21 B stars. If somebody is interested, it's beautiful data from the Dome telescope. But it's all stars that are supposed to have all these emission lines, but they just too bad. So they are new B stars. That's nice, but it's not what we want. Anyway, so if the extinction is such a nuisance, can we go outside of our galaxy, so we can look at galaxies more or less face on that don't have too much extinction and look for the same yellow things? Well, this is another quest. We actually look for any yellow giant or supergiant in the HST archive to make a catalog. So in this catalog, we have 200,000 candidate yellow giants and supergiants. Again, we cannot handle the extinction, but more or less we select the parameter space where they should be. And we have looked in ZPF, for example, or we're doing for other surveys, which ones of them are brightening. And this is, a result of 16 candidates. We are taking spectra with GTC. Like some of them are actually, again, blue, but some of them look generally yellow. And that gets me very excited. Maybe it's just like genuine variability in yellow supergiants, but my hope is some of these will actually blow out, in the nearby future, hopefully. So there is a peculiar case where we actually got to see a system. And this system was a bit puzzling because it was a bit against our expectations, This was a paper that recently we published with some collaborators where there was a transient in M31 that seemed to be brightening over the last years, also in the infrared, which we know that these luminous red nova used to have dust and so on. But yeah, it looked like it was brightening in all the bands. When we looked at the location of the progenitor, it looked like it was an AGB star. It was like some sort of 7 solar masses expanded AGB star. And it was like, oh yeah, look, finally. We didn't have any progenitors in this parameter space because they were obscured, but perhaps this is one, and because our expectations were that you have the companion and enters very slowly the layers of the expanded star, so it takes a lot of time to actually do some work on the envelope, right? Because the density is so low, so it would take years and years and years for this companion to inspiral and make some sort of merger event, which would take more years, so we really believe that this was, the actual full common envelope ejection from an already expanded star. So we got very excited. There was a paper and so on. But then, against our expectations, very recently it blew out as an optical luminous red nova. Again, plateau duration of 100 days, like all the other ones. So it's like, oh, damn it, it's like we thought we understood something, but we don't, so maybe we should look into something. But this event seems that it's actually very promising for us to kind of learn more about all these ejection processes, because this is definitely a very dramatic and hot outburst. All right, so what about spectroscopy, right? So if we look at the family of luminous red nova, we see that they spread hugely, between like low luminosity and high luminosity. This is generally correlated with the progenitor mass because they have more larger envelopes, there's more energetics involved. But we also can look at the spectra, and it's quite interesting because, and this goes for the supernova group here, right? Like at early stages, they are very similar to like type 2N supernova. They are hot, they have narrow lines. So many times when somebody observes one of these and they take one spectrum at the beginning, they put it on this transient namesaver and say type 2N. Adios. Nobody's interested, well, maybe some people. But then, of course, like if you look at the luminosities, they are not type 2N, they're like way below, they are in the gap. But people don't check that, But anyway, so with the spectroscopy alone, it's a bit hard to say at the beginning. Then as they start to red, they become more yellow. And the final stages is unlike any supernova, right? There's no radioactive decay. There's no energy injection that can pump up like the temperature, can destroy molecules. Here we have a huge formation of molecules like vanadium, titanium oxide. It becomes super red. Like you can see here, all of it is like in infrared. The optical has disappeared. And so like we really need to follow these things until the light comes. So then what can power this light? Well, one of the current models is recombination energy. If we eject a huge amount of hydrogen, each layer, at one point it will recombine and it will recombine, and the contribution of individual recombination layer can power this big plateau. Okay, that sounds reasonable. We eject hydrogen, hot, ionized, recombines, powers plateau like in type 2 supernova. Good. So what if we apply this model to existing luminous red nova? This is a one-to-one correlation, donor mass, ejector mass. Okay, for these guys, fine, but look at these guys. You need more ejector mass to make enough hydrogen to recombine to power the light burst than you have in the star. So obviously this doesn't work. Okay, so purely recombination cannot work to power these transients. So one very efficient method is shocks. Right? So in terms of shocks, we have been recently had like some simulations which also confirm like what analytical models predicted like nearly years ago, right? That shocks are necessary for these transients to explain the high luminosities and like likely the higher duration plateau, because first you have kind of hot material that cools down, right? There's thermal energy release, but then this energy that is transferred through the shocks is basically kinetic energy of this ejecta, shocking any kind of distribution of material, gas, torus, shells, whatever, that the companion or this system made, right? So if we look at some binaries in the Milky Way, like Beta Lyrae, for example, that's a mess. Stars are messy eaters. They have this, have jets, they have shells, they have like whatever you like, the heck you want, So all that material is just like flying around, So when you have a fast ejection of material during the merger, all that shocks whatever was existing before. So you have CSM interaction. So in these 2D radiative simulations, for example, this is like no interaction, but if you add interaction with some of like toroidal mass distribution, you can put a radius closer or larger, of your interaction. But the point is like you start to reproduce, and these things are observed events, you start to reproduce the light curves of observed events. And that is important because in quite a few of these cases, the amount of mass that you have outside needs to be larger also than the mass you eject, right? So even with that tiny ejecta mass that we can estimate, let's say from progenitor models, we can already explain this luminosity. We don't need a lot of hydrogen to recombine and shine. We just need a lot of mass around the binary in the torus or something, and then a little mass with high velocity just impacting this and transferring this kinetic energy into radiation. So yeah, for spectroscopy, this would be like the picture, right? The slow precursor wind from L2, from whatever process it is, and then the fast ejecta with shocks. So from every time spectroscopy, we can see that already, yes, shocks are confirmed, right? If we look at this type 2N supernova, like we see electrons scattered, right? And that means that you have an optically thick photosphere, which is ionized, which is bumping, like the photons, right, that appear from behind this photosphere, that you're increasing, the velocity dispersion in the wings, And also you have a ratio between H alpha and H beta of 1. And this is not a ratio that you get with pure recombination, right? You need an extra energy into these blue photons so that you pump up the ratio. And another evidence that there is some CSM, likely in this, is that when we get higher resolution spectra and we look at the lines of H alpha and H beta, right? This is our friend, the score, the one that we know is for real. And here we have like higher mass. We all see that they all have this narrow kind of component of absorption. And of course, this should ring a bell, because if you have like this disk, and the disk is kind of thicker, right? Like it will obscure part of the emission that comes from behind. So this disk is moving slowly, so it's a narrow emission. So then, like, well, this shows like we likely have this, which is obscured part of the viewing angle, and that shows that we have shocks at early. So I'm really excited because that makes some sort of connection between supernova world and the world of these stellar mergers, because like some of these CSM interaction mechanisms are very similar. Okay, so let's go into the remnant. So if we wait a little bit, we can also observe these events in like millimeter, radio, mid-infrared, and we can actually learn some things. In this case, it's our friend again. We have this recent work observing it between 9 and 12 years. And what this is, there's like two lobes, right? There's like, looks like there is some sort of like, well, jets, but like the bimodal ejecta from here, and like one of the edges is actually interacting with some pre-existing material and created some HCO plus molecules, which has been associated with shock. So yeah, in the center we have probably something, maybe we cannot resolve it, but then these lobes, which, when you eject a spherical ejecta into like something which has a disk, of course, it cannot go sideways, it needs to go, on the lobes. So then we do see these lobes expanding from the center and actually interacting with some pre-existing merger material. Yeah, this is another event. Actually, there was like the first event that had a red supergiant progenitor, but we never had more information than this. So people didn't really study too much because we only had the light curve and that's it, because it was recovered from archival searches. But some recent work was obtaining a full SCD, from all the way from infrared to radio emission to actually see what's going on inside. So first of all, it looks like the disk model doesn't fit, so there is no disk. There's nothing important. But what they see is that there is a shell. And this is a bit puzzling because, yes, we knew that there would be mass transfer and other things, but it really looks like whatever the merger ejecta is, it's still here very confined in the center, expanding with like the velocity was supposed to be expanding with a few hundreds of kilometers per second. But then there is a lot of some sort of pre-merger material around this stuff, which is like, I think it's around like 10,000 AU or something like that. And it's very cold. So yeah, we still don't understand where this mass comes from. So there is a puzzle. We thought that you start transferring mass, it's a little bit, and then you go into the burst. But this shows that in this system, there is some mass very far away, which was ejected by the system long time ago. So it's new questions we need to explore why there is this here and how we can explain that. So we can also look for other objects. These are luminous red novae in outer galaxies and 31 with different progenitor masses. This is the least massive, this is the more massive. And then we can see how the dust looks. So we had a GWST proposal where we could observe and model these SCDs. There were some spectra, which shows clearly there's some molecular emission here. So we could estimate how much dust this luminous red nova would make since their peak. And for comparison, this is core collapse supernova. And we can see that we start lower than this, but they really ramp up by a lot. So some recent simulations actually show that most of the dust from this luminous red nova form between 10 and 20 years after the actual merger. And this is very short timescales. Like for supernova, it takes years and years and years. And there is a reverse shock, so we cannot really explain this fast formation. But luminous red nova are very efficient in making dust on very short timescales. So this is quite important because if we want to make a lot of dust, let's say in the early universe, we need something that makes it really fast. So these are like one possible promising channel for making this dust. So yeah, our problem is like, for example, some models show that the ISM has too much dust, right? These are the measurements. And we need contribution from AGB stars, which are smaller, but there's a lot of them. But we also can have supernova, which eject all this mass, but then they have reverse shocks. And these reverse shocks can splatter the dust grains, they can destroy them. So the dust formation is suppressed, So to explain what we have nowadays, we need supernova and no reverse shocks. And well, this is not very realistic. So, I'm happy about this because, maybe we can plug in and say, okay, maybe we should look into binaries as well, right? If they're so efficient in making dust at such a small times, we also have mergers between any masses, small masses, big masses. So, the small ones are contributing similar to AGB, the big ones similar to coalesced supernova, and they have much weaker shocks, right? This is not like supernova energies. This is like 2 kilometers per second. As I mentioned, it's very a walk in the park, This is like not like a supernova. So the shocks are much weaker, so the dust grains are way more likely to survive. So looking into the future, I could not stop without this. We have LSST, it started observing. We still aren't sure about the schedule. They say maybe in spring some of the alerts will come. So if we want to progress in this field, of course, we need new surveys, new data. We need to find more luminous red nova, find their progenitors and study and detect them and so on. So yeah, we want to use new surveys. So LSST is promising, hopefully starting soon. But, there's a problem. 10 million of alerts per night. I don't have enough PhD students to look at all of them. So we need strategies, right? So we need a very efficient filter which can decrease 10 million to 1 or 2 per day, that we can open our email, look, yes, no, let's trigger a follow-up. So this is at the moment not only our problem, it's the problem of many people who are doing transient. So, well, I hope this may be of use of you because we kind of prepared for this little bit tsunami of data. So we compiled a catalog of about 8 million galaxies up to 2 gigaparsec, which, as you can see, there's different catalogs, existing ones, but they cover different regions of the sky. And some are more complete in the far distance, some are more complete at shorter distance. So none of them would satisfy us. We like to be lazy. Well, let's put it this way, efficient, better word. We have only one catalog. And if we see a transient, what is the distance? We want a gap event. We want a gap event because we know our luminous red nova gaps. So if they have less luminosity than supernova, we will care about them. And how do we know that? Well, we need distance. So then the best way is we can combine many catalogs, and then we can combine their, let's say, photometric distances, because that's kind of a lot of them. And here you can see that with 3 distances, you actually reduce a lot your uncertainties. If you have 1 photometric, 2 or 3, you get closer and closer to what the spectroscopic distance is, right? You make an average of them, different teams have different methods, you remove outliers, you do all kind of things. And then basically your final estimate is much closer to actually the spectroscopic distance. So we gain with that. Plus, let's see, yeah. So we also combine ellipses, and this is actually cool for time domain, because normally what we do is to sort of matching for transient within this ellipse, is inside this galaxy or it's inside this galaxy, it's in the core, it's outside of the core, so all this is in the catalog. And because we care about underluminous things, we can only see them at closer distance. So we actually bothered with the whole team to clean it for up to 100 megaparsec. So they were unresolved binary stars, some other things, the machines tell it's a galaxy, you see it, it's not a galaxy. So, this catalog is way cleaner than the existing ones because we looked at it. So I hope this is of use. If you want to use it, let me know. And with this, I come to my conclusions. So I hope I convinced you that the universe is made of stars, but not only single stars, but binary stars. And we should care about how they evolve and how they interact with each other, because this alters many things, right? Along this path, there are many uncertainties that we still don't know. But when we see a binary which is actively interacting, now we have a chance to learn something about it. And these are these astrophysical transients, luminous red nova, that they kind of allow us to peep inside what's happening within this common envelope and what happens after and before as well. So we can look at their progenitors to see what is the parameter space of unstable binaries. We can study their precursors to see this build-up of L2 mass loss, and all the shocks leading to the final merger. And we can also study the properties of the outburst to see what are the energetics, what is powering the light burst, and also how this ejector is kind of populating the dust in the assay. So, well, actually, this is the C3PO signs of my ERC project. So, yeah, thank you very much.
Thank you for a very nice talk. Are there any questions from the audience? Yeah.
Probably stupid question because but you show this diagram where you have this conical shape from the Gaia with all the possible luminous red novae, and then you did some follow-up to see, and you turn out that most of them are like all of the stars, right? Because of extinction in the galaxy.
Yeah, I mean, we tried twice, we kind of failed.
But so which is the fraction that you expect to be obvious? Because that means that most of the stars there are probably OP stars, just with high extinction, right?
Yeah,
That's the conclusion. Does that affect the population of all stars in the galaxy? Because here you have a lot of them, or
yeah, we have not attempted to do the statistics. Yeah. Yes, no. We just kind of looked at which ones looked within our parameter space. But I guess it's consistent. I mean, like these Hertzsprung, like stars crossing the Hertzsprung gap, it's a short-lived period that it's really unpopulated. So if your extinction is done right, like I think the amount of stars we should find here, it's way less than we actually see, like on a first approach. And it's because many of these main sequences are actually scattering in there.
So how many of them do you find? There was not clear to me. There were like luminous.
No, I mean, none of them so far looks, I mean, from this sample, they're OBE, I mean, from this previous one, we did not look for,
Yeah.
Oh, yeah, this one. Yeah. Yeah, I mean, from here, like the previous one, we looked for brightening events. And B stars have long evolving light curves, unfortunately. They have this build up. For these guys, we did not look for brightening, but just for variability. Because in this case, we wanted mass transferring binaries, perhaps not like 5 years before the luminous red nova, but just actively mass transfer. So yeah, because I mentioned like when you observe like nearby mass transferring stars, they have H-alpha emission, they have shells, they have disks, they have all this kind of stuff. We try to include this in our search criteria to try to identify them. But yeah, as you see, like in the cases when we got spectra, we have, I don't know, a very small fraction of this initial sample is actually kind of yellow, like G, F, A type stars. The rest are just, only with extinction.
Okay. I have a question related to that actually. Did you check a similar sample in the Magellanic Clouds? Because we actually have a catalog of 9 million Gaia objects in the LMC. So you could make this diagram for the LMC, no? And then you have less probability of extinction. Did that work?
Yeah, I mean, now what we're doing is like we have these catalogs of yellow giants and supergiants from like HST and other surveys. So we are actually querying like well, not ZTF because it's in the north, but yeah, we have like Black Gem, Atlas, and other surveys. So we are actually doing this. Like we're taking the position of known yellow kind of giants and supergiants, and we are like retrieving all of these light curves to make some sort of statistical analysis to select possibly the ones that are slowly brighter.
Right, finding new ones using this technique, I was thinking.
Yeah.
No, you didn't try that with Gaia.
Yeah, no, well, not
For the LMC.
Yeah, not inside it. No.
No, okay, all right. Yes, yeah.
This is totally different, so forgive me if this is a little bit beyond, but in primitive meteorites, we find that there are transient heating events that result in evaporation as well as melting. And I'm curious what the timescales of the shocks that you propose are and what kind of thermal consequences may be as a result of those thermal shocks.
All right. I mean, I think, well, the shocks is days, years, right? Because you have all this circumbinary material and the ejector is kind of crashing and plunging through it, but like eventually the shock dies because it's kind of like.
But then there would be another shock that would come through, no?
Well, I mean, if you think that you just eject part of the envelope, then in principle, no.
No.
Now, of course, this has implications that then if a supernova happens, like 1987A, which was supposed to be a merger, it will have a ring around it, right? So then like the supernova may crash into that ring as well. So
Okay. And what kind of temperatures might be achieved by
yeah,
these sorts of shocks?
I mean, I think this probably could find this in the paper that does the 2D simulations, but I would not know by heart. Yeah, like this paper, like it's very recent, Kirillov and all, so they have like some diagrams where they have the temperature of the shock actually inside.
Muy bien, thank you.
Yeah, actually, this thing, but yeah, one was temperature, I think, one was optical. That I
Okay.
Thank you.
okay.
Yes.
Okay, nice. So, thank you so much. So I imagine there's sort of in our modeling that the starting point is formation of a jet from whether progenitor, either master star or removal from the star from the star of echo. So I guess my starting point is from your ending point, and I was wondering if in this shock the model produces so that the big also not only output but X-ray and maybe gamma outputs.
It's difficult. We look for X-ray here, we look for radio, and we don't see anything. And I think because there are two things, like the velocity of the shock is like few hundred of kilometer per second, so it's not very energetic shocks. And also that part of the shocks is actually hidden, like behind the photosphere, right? So there's a lot of gas, and the shocks happen in the inner part. So they have to get out. So then they die mostly. So the X-rays like will not crash. Yeah. So
Okay, I guess you know also that it's the output of not that coming out.
it depends on who you ask. If you put some MHD in your simulations, you can get some jets in this event. But they're very kind of gentle jets, right? Again, a few hundred of kilometers per second, like not like relativistic jets. Yes,
How long takes the common envelope phase?
that's a good question.
Well, I'm because you are looking at archival data to constrain the progenitor. But could be that the progenitors that you are constraining are already in interaction with the companion.
It's possible, yeah.
The expectations that you are having fine progenitors and the thing that you mentioned that they are just merging, but you were talking with this result, maybe because of that.
Yeah, I mean, this is one of our assumptions, right? When we see that like the light curves, it's quite steady, or here we did not really detect much, or the above event, right? Like we see some years of kind of a flat light curve where the progenitor doesn't change much, right? The photometry is more or less stable, and then a few years before it starts to evolve. So this is an assumption we need to make. Of course, if before, during the steady state, the system already had some outflows or some pseudo photosphere, some extra things, then what we're modeling is completely wrong. Yeah, I agree. But because the progenitors are like not changing over the years, but just in the last year, we assume that the change is due to this L2 mass loss, which it's very quick in shrinking the binary, right? Like the loss of angular momentum through like the the outer Roslow points is very quick. So basically, we assume that first you see mostly the donor star, which is the more evolved and expanded, which dominates the light. So we model mostly the donor star. And then the L2 one, yeah, when you start increasing your luminosity, of course, it doesn't make any sense to model that system because it's not your star anymore. It's your star and some like extra luminosity from disks or from other accretion or something.
About the rate, you said that the luminous red nova rates are similar to coalesced supernovae. So where are they?
Where are they?
The luminous red nova, because we find very few.
Exactly, but because they're very faint, right? So let's say with the luminosity, I think that.
So how the rate was estimated?
Yeah, you see, like here it's something like ZTF, right? So this is the observable distance with something like ZTF. So we mostly go up to like 100 megaparsec. So the rate was estimated from ZTF, right? They try to spectroscopically classify anything that would be within 100 megaparsec. So it's a spectroscopically confirmed, like for anything that would be in a volume limited survey. But of course, if something is very faint, you're not going to even detect it, at 100 megaparsec. It has to be much closer. So we detect very few because they just like intrinsically faint. It's like some of them are just like novae, bright novae, and we see novae in like M31 and maybe a couple of other galaxies, which is super close distance to us because they are just not detected. Like LSST will probably change the game, yes. It will increase, but then spectroscopically confirmed for LSST is going to be a real challenge.
I found very interesting talk, so congratulations. In particular, I wondered about all these tasks that was very quickly produced around the merger. And I have two questions. First of all, I will ask, for example, if at that specific time, you know more or less the outflow from that star has a specific composition. And the other question is if you can, from a spectrum, try to infer, for example, absorption bands, the composition of that gas, if you have tried to do that.
Right. So yeah, this comes to the aim that we have. Yeah. So to understand the system before the merger, we should catch it in this phase. So yeah, this like we are trying very hard with our team, right? The only object that was caught is this M31, and this shows the spectra, right? The spectra was taken for this object. It agreed with a very cold evolved star, and it had like two components in the spectra. It was like a hotter star and then like a colder component, so like a binodal component. So I don't know if the resolution of the spectra was enough to infer a lot about composition and so on, because this is like M31, so likely was like very low resolution. So I mean, you really need to kind of predict the burst to trigger all your follow-up at this stage to actually learn. So we are trying to do that, but it's hard.
We can try to discuss this. Yes, thank you.
But maybe with all these archival surveys, I mean, this is what my hope is, Euclid. Like LSST will have archival data. Like then you'll have, the first that is an X-ray Roman, right? Like all these things are going to provide us a map. But if something happens in the future, you can always go back and look with high resolution, very deep data, what was there before. So that's going to be our, lifesaver.
Okay, yes.
A little bit along the line of what Jose Maria was asking now, because when we look at that from isotopic compositions, we can kind of infer, if this comes from AGV or this comes from supernova and so on. You mentioned that these could be potentially large contributors to dust and so on. So, and you have some modeling with MESA and so on. So you have an idea, at least from the theoretical point of view, what type of composition you expect. So
it's mostly silicates, yeah, because all these massive stars.
But in terms of isotopic abundance, is there specific signature that could help you differentiate from other sources of dust.
Yeah, I mean, we haven't looked at this ourselves, but for some galactic objects, the near-infrared spectroscopy had some different isotopic composition for aluminium, right? Aluminium 26 or 27. So, yeah, so, so then they could differentiate the emission bands of aluminium oxide by the isotopic.
Factor is not the same, probably depending on the temperature. It's not, you can get the beginning some amorphous silicate and then get the crystalline. And even when you have a really hot environment, probably you end having refractory oxides, like the CI calcium aluminum inclusions, you know. So it could be really nice to see in the, depends of the resolution for sure, but we can take to look at the data.
Right, but I think what Aldo is saying, to tie it to a class of objects that have been detected in the solar system. Also, they have this oxygen isotope diagram where the solar system composition is in the middle, all focused on the central composition, and then there's all this extra solar composition. So many of them have been identified, AGB star, supernova, whatever, but there are some unidentified. Where the stellar source is not known. So it will be interesting.
That's interesting.
You know, the papers that Larry Midler is writing and so on.
Exactly.
Condensates for very quickly. Once you have the outflow, then have reached a point in that the solidification is done.
I mean, what we believe is also because you have like shocks that can help compress further the material, right? So after the shock energy dies out, you have a way more denser region that can enhance like nucleation. So, I mean, but yeah, we need some models for that.
And something repeatable, because we see evidence of the same object being heated more than once. So that's part of why I like your model, because you can every few days or every few 100 years you have another pulse, and then what we see in the igneous droplets would start to make a little bit more sense.
So one of your system gets like a peak of heat every one.
So we have conduls, for example, that show that they have been heated and melted multiple times, and we need something on the order of days to hundreds of years in order to explain that. Right now in the community, we are pretty pleased with sugar on top. Bring us the process that can help explain this.
In fact, at the very beginning, the entire solar system was magnesium rich. All silicates were magnesium.
Yes.
But little by little, because of all this overheating, the iron oxide went into vapor phase and then it started to interact with the phosphoritic melted conduits up to the point in which you have iron rich conduits at the end. So there is two generations of conduit like material.
Because there's the aluminum rich conduits too, so maybe three.
Yeah, three.
I guess these enter also like second generation planets and so on. Like you also, if you have these material being ejected, it also can make like some planet, because that's a torus, it's gravitationally bound, it can fragment, it can collapse, it can make
You need about 100,000 years for that.
Well, I mean, the first stars in the Milky Way doesn't have that. But yeah, this is a bit out of
All right. Maybe this is a good point to stop, because we are starting to lose some of the audience, perhaps.
You got the dust people excited.
Yes.
Wow, that's good.
Well, let's thank Nadia again. Those of you who are joining for lunch, we are leaving a few minutes before 1. Yes.